How many grad students pretending to be undergrads? Okay, so I'm going to try and give a talk that is accessible to all groups of students. It will be up to you to determine whether or not I succeed. So I will give you my standard warnings when I do this sort of thing. And those of you who have had me for a class have heard these many times before. I do math because I like to do math. I sometimes get enthusiastic. I sometimes get carried away in the way that an out-of-control locomotive can get carried away. If that happens, you have to slow me down. Questions are good for slowing me down. You can send tweets to the talk hashtag to slow me down. I'll be checking periodically. If you're going to throw something, it has to be soft. No bricks, no hard edges, no knives, no balled up pieces of paper at worst. Okay. So, infinity. I like infinity. And one of the reasons I like infinity is actually a very slippery notion. So I'm not going to actually start off by defining what I mean by infinite. I'm going to start off by defining what I mean by finite, move from the finite to the infinite, and then see where we start running into trouble. So, finite. We have to start somewhere. I could actually start from the very beginning, but then we wouldn't get to the start of the talk until about halfway through the semester. So, given that this is a general talk, I am going to lie to you at times. I'm going to be a bit imprecise. I'm not going to worry about covering all the bases. If you want further information on how to make some of these things precise, let me know and I'll point you to places to go. So, I lost the opportunity for that. Okay. So I start off with a set, and I'm not going to define what I mean by a set, because defining set is one of those incredibly hard things to do, actually. It's remarkably difficult to define what we mean by a set, even though we use the notion all the time. But I'm going to define what I mean by finite. So X is finite. And like I said, I'm going to start with stuff that we know. So I'm going to start knowing natural numbers. So X is finite if there exists a natural number. Now, this is one of those things where people differ on different sides of the Atlantic. How many people think the natural numbers start with 0? How many people think, more correctly, that the natural numbers begin with 1? Okay, good. I don't have to fight 2. So, my natural numbers start at 0. The natural numbers end 1, 2, 3, 4. The counting numbers, it's very hard to count 0 of something, in my professional opinion. So, satisfy it if there exists some natural number or zeros, so that basically, I want to formalize the definition of I can count the elements in the set X, and there are n of them. So if X is in bijective one-to-one onto correspondence to a set I will call, for lack of a better term, bracket n, which is just the numbers from 1 to n. 1 increasing up to n. So I have to tell you what I mean by bracket 0. Which I mean to be the empty set. So bracket 0 is a set that has nothing in it. Bracket 1 contains 1. Bracket 2 contains 1 and 2, etc. So this is just telling me how many things there are in this. Are we happy with that? How many people are still happy? Not everyone's put up their hand. Okay. So, finite set is a set where we can count the elements. We can define an infinite set then to be a set that's not countable. Sorry, X is not. Okay. If we go back to the definition of finite, something which I didn't do, which I will leave for you to do because I'm not going to do it. is if I say that a set is finite, so there is some n, so that x is in one-to-one correspondence with the numbers from 1 to n. But you actually then have to prove that the n is unique. The number of elements in a set is a well-defined notion, that I cannot have a set that's bijective in bijective correspondence with the set 1 to n, and also in bijective correspondence with the set from 1 to m, where m and n are different. It might seem obvious. The proof is not difficult. I'm not going to give you the proof. I'm going to leave it for you guys to do. But you actually, as you go through these arguments, these are the sorts of things that we actually need to make sure, the bases we need to touch in order to actually demonstrate that the notions we're dealing with, the things we're defining, make reasonable sense. Okay. So a set is infinite if it's not finite. What do I have? Ooh, I'm not going to talk about that. Okay, so one of the difficulties with giving a talk to an audience that ranges from first-year undergrads who've been here for 2 weeks and are probably still feeling a bit overwhelmed by this whole university experience thing, to graduate students, some who've been here now in their 4th year and have seen a bit of stuff, is that I'm always going to hit things that some people have already seen and other people have never seen. So I'm going to drift, whenever I have the opportunity, to the side of the people who know less, rather than to the side of the people who know more. So I want to give some examples of infinite sets. So one obvious example is the natural numbers themselves. I claim that there are infinitely many natural numbers. I will leave you to see why that's actually an obvious claim. An obvious is one of those words that when a mathematician uses it, you should always get this little cold feeling in your soul. Because it's not necessarily clear what they mean when they say obvious. I just have to cover my Twitter feed. I claim that the set of all integers is an infinite set. Now, can someone give me a slick heuristic argument why the set of all integers is an infinite set? If I know that the set of natural numbers is an infinite set. Exactly. So this is infinite. Since the set of natural numbers is infinite and the set of natural numbers sits inside infinite numbers. Sorry, sits inside the set of all integers. The set of rational numbers, quotients of integers, a over b, where a and b are integers and b is not 0. I claim that that's an infinite set. The set of all real numbers, I claim is an infinite set. Take the set of real numbers so that there exist a naught up to a k in the integers with a naught plus a1x plus a k x to k. How many people have seen this set of numbers before? How many people know what the A stands for? It does not stand for Anderson. So what I'm looking for are the numbers that are solutions to polynomials with integer coefficients, roots of polynomials with integer coefficients. What sorts of numbers, what's the name for a number like that?
Algebraic.
They're the algebraic numbers, exactly. And this is an infinite set. Okay. Some examples of infinite sets. And now we can ask a question. The way I defined finite was I said a set was finite if it was in bijective correspondence to effectively a set we know. So now I can ask, well, I have a bunch of different infinite sets. Are they bijective to one another? Are they the same? You know, should we define, can we define size of an infinite set? And that's really sort of what we're going to spend a lot of our time. Talking about. Can we make sense of a notion of size for an infinite set? If we can make sense of a notion for size of an infinite set, what happens? What do we get out? What is it standard? Is it weird? What goes on? So, again, I'm not going to be too technical. Let's just say infinite sets. A and B, same size. Or here, I'm being loose. If there is a bijection. Between A and B. How hard can it be? How many people don't know what bijective means? How many people don't want to admit in front of other people that I don't know? So what bijective means is, so I have a function between two sets. And I can basically ask, how good a correspondence between these two sets does this function give me? So bijective, and I'm going to spend a bit of time on this because this is the critical notion for the next. The joke I was going to make at the beginning is, how long do I have? They told me I had infinitely many minutes, but yeah, that was the answer I was expecting to get. So bijective is composed of 2 bits. Injective, or one-to-one, and surjective. Which is onto. So what is injective? Well, in words, F is injective if things that start out different stay different. So if I take 2 different numbers in the domain, in the A, and I apply my function, I get 2 different things on the other side. So if I have A and B and A, which are different, and I apply F, then what I get out is different. Squaring on the real numbers is not injective, because 1 and minus 1 squared both go to 1. So minus 1 squared is 1, 1 squared is 1. So if I'm just squaring on all the real numbers, I have 2 real numbers that end up having the same square. That is bad. From the point of view of today, that is very, very bad. If I look at squaring just on the positive numbers, it is one-to-one. Because if I take a positive number and I square it, well, I'm going to get a positive number. I can then take the square root, and that tells me exactly what it is I started with. As long as I'm not allowing myself to square negative numbers as well. A function from A to B is surjective if everything in B gets hit by something in A. Hence the word onto. Pretty sure the A is just your. Okay. So if we take some element in B, then it's going to get hit by something in A. Then there is A and A, or F of A. So if I have a bijection, what that means is different things in A goes to different things in B. Everything in B is hit by something in A. And so I could think of, if I listed out everything in A and everything in B, I am just being able to pair up something in A exactly with one thing in B and being able to do that for everything in A. So I have, all I've done is I can think of as B is as a copy of A where I've just changed the names of everything. Good enough to start?
Yes.
Okay. So if we use this definition that sets, infinite sets are of the same size, or that sets are of the same size in general, if there's a bijection, it works for finite sets. Finite sets are of the same size if there's a bijection is just saying that this, in this board I've erased, if I'm taking a set being finite, if it's bijective to 1 to n, it's just saying that that n is well defined. If I have bijection to 1 to n and bijection to 1 to m, then the m and the n are the same. But what happens with infinite things? Okay. I have a list, a definition. Remember which things are on the list. Okay. So let's look at set of all integers and the set of positive integers. So I claim that there's a bijection between them. Now if I'm going to claim that there's a bijection between them, I have to do one of two things. Either I have to write it down for you, or I have to invoke mathematical machinery that implies that it exists, even if that machinery doesn't tell us exactly what it is. So here, I can actually do it directly. So n, I have 1, 2, 3, 4, 5, 6, 7. I can list the positive integers. Now what I cannot do, if I want to have a one-to-one correspondence with the integers, is I cannot start with 1 and 2 and 3, because I've got none of the negative numbers appearing. 0 doesn't appear. I've got a problem. But what I can do is I can be clever. And I can write down the integers in a slightly unusual way. So I start with 0, and then I do 1 minus 1, 2 minus 2, 3 minus 3, etc. Every integer shows up on this list somewhere, and it shows up on this list once. And then my bijection between the two is just the one that comes from matching up things in that list. If you would like a challenge, if you get bored in the rest of today's talk, heaven forbid, in a lecture tomorrow or Friday, as long as it's not mine, on a bus, you could try and figure out if there's a formula for this. If I can write down what the integer is as f of n. If you have a formula, then it's really easy to check things. Here I don't have a formula, I've just listed a correspondence. I can check that it's injective. That's fine, because this list of integers is just all the distinct integers. It's surjective because every integer appears on this list, so I now have a bijection between the natural numbers and all the integers. Are we good with that? Because in a minute, things are going to get weird. Slippery weird. Okay. In mathematics, we have classical examples, folk tales that we pass down through the generations of little stories that every generation of teachers tells the students that come after them. And then those people, when they become teachers, pass them on. How many people have heard of the Hilbert Hotel? Those of you who haven't, this is where the Hilbert Hotel comes in, this whole discussion of sizes of infinite sets. David Hilbert, one of the greatest mathematicians of the late 19th, early 20th century, packed it in one day. He'd had enough. tired of university admin, tired of students. Just goes off and he starts running a hotel. His hotel has infinitely many rooms, and those rooms are indexed by the natural numbers. So there's a room 1 and a room 2, and it takes a long time to walk down the hallways to get to room 5,473,612, but you can eventually get there. And his hotel is full. And then a coach pulls up with infinitely many people in it, all needing a room for the night. Does he panic? No, he's a mathematician. There's no need to panic. He says, not a problem. He takes everyone who's currently in the hotel and he moves them to the room whose room number is twice their current room number. So the person in room 1 goes to room 2, the person in room 12 goes to room 24, the person in room 1003 goes to room 2006, and all of a sudden he has infinitely many empty rooms, and he just takes the people off the coach and puts them in the empty rooms. And what he was doing is he was just using the fact that even though it looks like 2n sits inside n, where by 2n I just mean even numbers, even natural numbers, these two are actually in bijective correspondence with one another. I have lots of room. I can do all sorts of things. Infinite sets can have infinite sets sitting inside them. Okay. Now, what about the natural numbers and the rational numbers? The natural numbers look vastly smaller than the rational numbers. When I look at all possible fractions, I have infinitely many fractions just in the interval from 0 to 1. In any sized interval, I have infinitely many fractions. It looks like the rational should be a vastly bigger set than the natural numbers, doesn't it? How many people think the rational numbers are a vastly bigger set in any quantifiable way than the natural numbers? How many people are scared because of how I asked the question? One of the things that you will learn over the next few years is that your intuition has a tendency to lie to you. And part of what we are learning as mathematicians is how to temper the fact that we work within a series of rules, some of which we can bend and some of which we can break, but we have to learn how to harness, how to moderate, how to ignore sometimes our intuition when our intuition is going to lead us astray. So what I'm going to do first is I'm going to look at the natural numbers and the positive integers. Because if I can show that the natural numbers are in one-to-one correspondence with the positive integers, then I can use this same sort of trick to get that the natural numbers are in one-to-one correspondence with all of the integers. So first thing I need to do is I need to list all of the positive rationals. I need to list them in a reasonable way. So the way I'm going to list them, I'm going to make a grid. Numerator, denominator. So the numerator can be 1, 2, 3, 4, 5, 6, all up. The denominator can be 1, 2, 3, 4, 5, 6, etc. And then I won't do all of the positive rationals because that would take some time. And then I just write down all of the rational numbers because I know what the numerator is, I know what the denominator is. Etc. Now what I do is I go through and remove duplication. Because I have duplication here. 1 over 1, 2 over 2, 3 over 3 are all the same number. So now I go through and I remove duplication. So I remove everything where the numerator and denominator have a common factor. Those are the ones I remove. And now what I do is I walk through and in my walking through I get a bijection between the rationals and the positive integers. So this maps to 1, that maps to 2, that maps to 3, to 4, to 5, to 6, to 7, to 8, to 9, to 10, etc. So I now have a way of associating, in a one-to-one way, distinct positive rational numbers, and every positive rational is on this list somewhere, with the positive integers. So I have written down, schematically, a way, a bijection between the positive rationals and the positive integers. And someone has now anticipated my next question. Can we always do this? If we are sufficiently clever, if you hand me any infinite set, can I always find a bijective correspondence between that infinite set and the natural numbers? Because if the answer is yes, I can do that and we can be done. Because that would be it. There would be one size of infinity. Infinity would be a well-defined notion. We could all go home. It's Wednesday afternoon. No one's got a class left today, right? So I could have gone for infinitely many. Except that I have a meeting at 2:30 I need to get to. Organized, so you're safe. So now let's look at classical example. The natural numbers and the interval from 0 to 1. I claim that these are different sizes. They're both infinite. I can see a copy of the natural numbers in here by doing a variant of just taking 1 over n. It's not exactly taking 1 over n because 1 is not in that interval. But 1 over n plus 1 would work, and that would give me a copy of the natural numbers sitting inside that interval. But I claim that they are different sizes. And the way I'm going to prove it is I'm going to... So this is an argument that goes back to Georg Cantor, late 1800s, one of the developers of set theory, and an unfortunate victim of set theory because the sorts of things we're talking about, I'm going to be talking about over the next 20 minutes or so, drove him insane, sort of literally. Because no one would accept what he was doing. Alas. But we're mathematicians. We're stronger than that. And to be honest, we've had 150 years of getting used to some of these really weird ideas, and 150 years, time heals all wounds. So this is an argument known as Cantor Diagonalization. And yes, I still spell like an American, and I always will. My alphabet ends with a Z. That's just the way it is. So assume that I have a bijection between the natural numbers and the interval from 0 to 1. Assume I have them. Assume they are the same size. What I'm going to do is I'm going to construct a real number between 0 and 1 that's not in the image of this bijection. That's going to give me a contradiction because since I started off with a bijection, everything between 0 and 1 has to be the image of an integer, positive integer. But I'm going to build one that's not. And I'm going to build one in a very straightforward way. So that tells me that f of 1 is, it's decimal, so it's 0.x11, x12, x13, x14, etc. Where each of these xij's is a 0, 1, is a digit between 0 and 9. I'm just writing down the decimal expansion of my number between 0 and 1. I do the same thing for f of 2. It's 0.x21, x22, x23, x24, etc. F of 3, x31, x32, x33, etc. And I just keep going. And every real number, if I've started off with a bijection, every number between 0 and 1 has to be somewhere on this list on the right-hand side by the fact that I have a bijection. So now, consider. How many people in the back can see my hand? So consider. I now build a number by taking x11 and subtracting 1, with the proviso that if I started with a 0 and I subtract 1, I get 9. So I'm working in this set from 0 to 9. I'm going to subtract 1. If I fall off the left-hand side by subtracting a 1 from the 0, I end up back at the 9. So modular arithmetic, those of you who are in the first year taking Math 1001, number theory and cryptography, will experience this a bit later. And I just want to stay in the set from 0 to 9. So if I'm subtracting 1 from 1, I get 0. If I subtract 1 from 2, I get 1. If I subtract 1 from 9, I get 8. If I subtract 1 from 0, I declare that I get a 9. Are we all good with that? So I'm taking the diagonal, what you might think of as the diagonal entries, if I were to view this right-hand side as a grid. And I subtract 1 from each diagonal entry. And then I notice something. This number I've built differs in at least one digit from every number on that list, because I have made it so by taking the diagonal entries, taking one entry from each number on that list, and subtracting 1 from it. So this number is not f of anything. Line construction. There does not exist a natural number n with y equals to f of n. Because y differs from each f of n in the nth spot. I started with a bijection. I built something from that bijection to demonstrate that that bijection cannot exist. The only assumption I made was that there was a bijection. That assumption has to be wrong. So there does not exist a bijection. And so these two are different sizes. Beware of what happens when you assume. So, how bad is it? We now have two different sizes of infinity. I have the natural numbers, which I will call a countable infinity. And I have the interval from 0 to 1. But it's actually not too hard to write down a bijection between the interval from 0 to 1 and all of the real numbers. And so I have that the natural numbers, or the integers, the countable infinity, is of a different size than the real number infinity. Just how bad can it be? So I would like to demonstrate just how bad it can be. So what I'd like to do is I'd like to use a variant of this argument. So first, is everyone still with me? Roughly. So I've now got two different sizes of infinity. Okay. As I said, I'm not going to define what a set is, but let's take any set. And I'm going to define what we call the power set. Snappily denoted P of X of this set X. The power set is the set that contains all subsets of our set X. So it's a set of sets. So it's going to contain the empty set, because the empty set is a subset of every set, even the empty set. It's going to contain the whole set and a bunch of others. I can do this for a finite set. I can do this for an infinite set. And here is sort of the infinity generating machine fact. is that x and p of x are never bijective with one another. P of x is always bigger in any sense of the word. And it's basically the argument we've just given. So, let's actually see why this is true. And this is one of those arguments that still, even though I've been looking at it for really quite a long time. Yes, we have taken the blue pill. We are seeing how to beat the rabbit hole. Actually, isn't it the red pill that's the rabbit hole, and it's the blue pill that takes us back to the matrix? I can't remember. This is the fact that gives me a headache, because what it means is we start with the integers. We build the power set of the integers. We get something that's bigger. We feed that back in. We get something that's even bigger. Not only is infinity not a well-defined notion because there are already two infinities that we've seen, this gives us a way of building infinitely many different sizes of infinity. Just by each time I get one out, I just stick it back in. And I keep getting bigger and bigger and bigger and bigger infinite sets where I have a well-defined notion of what bigger means. Which is why we get the blah ha ha. So why is this true? And again, we start at the same point. We assume that we have a bijection between x and p of x. Now, since f of x is a subset of the set big X for any element x in the big set, the question is x an element of f of x? Makes sense. Little x is an element of the set x. F of x is a subset of the set x. And the question is an element of a set in a subset of the set is a question that makes sense. Yes? Everyone agreed? People are getting really nervous. That's not a trick question. Does it make sense? And if I have an element of a set and I have a subset of the same set, the question is the element in the subset is a question that makes sense.
Can you use A instead as the element?
I can use A instead of, yeah, okay. Fine. So f of A is a subset of x for an element A and x. The question is A an element of f of A makes sense. Is that better? People happy? I need nods. I need positive reinforcement here.
Yes.
Okay. So let's build a set we call Y, which is the set of elements A and X where A is not an element of f of A. Because this also makes sense. If the question is A in f of A, if that's a question that makes sense, then is A not in A is a question that equally makes the same amount of sense. Are we happy? We've now built a set. And it actually, in formal definition, it is a set because we're taking the set, we're applying a rule of things. It's the trick is not that this is not actually a set. It is actually a set if X is a set. We good? Oops. I guess I have to say one thing first. Since f going from x to p of x is a bijection, there is an element b in x where f of b is equal to this set y. Since I have a bijection, I have built a subset of x. Since I have a bijection between the set of all subsets and the set x, y is one of the things over here there is something that goes to y. That's the definition of a bijection. And then the question we ask is, spoil my own surprises. Is b in y? Because if b is in y, then b is an element of x where b is not in f of b, but f of b is y. So if b is in y, then b is not in y. But if b is not in y, then it's an element of this set, so it is in y. And we just go in it. We never get out of this loop. If the answer is yes, then it's no. If the answer is no, then it's yes. And then it's no. And then it's yes. And then it's no. It's yes. We never get. So something goes fundamentally wrong at this point. And the wrongness is not here. The wrongness is the fact that I built this bijection f in the first place. That allowed us to then go through this argument and ask a question which in any reasonable mathematical way makes absolutely no sense. And the only thing we can say is jack and run away. So there is no bijection between x and the power set of x. Now I can stick x inside the power set of x, because if I take any element in x, I just take the subset of x that contains just that one element. So I can see a copy of x in here, element by element. So this is at least, this number of things in the power set is at least the same size as x. But it's strictly bigger, because I can never go back the other way. Now there's a whole machine that I'm not telling you about, built around this stuff, because mathematicians have been playing with this for 150 years. We like this sort of thing. But I now have a machine for building as big an infinity as I want. And there are people who spend their careers, mainly people dealing with mathematical logic, who now start doing very subtle distinctions between different sorts of infinite sets. Constructible and recursively denumerable, and all sorts of things. I don't even know what the words mean. But there's now this entire zoology of infinite sets. But I want to come back to a basic question. So before I go on to the basic question, are there any other questions? Yeah?
What is the power set of the empty set?
The power set of the empty set is the set that contains one element, namely the empty set. So the power set of the empty set is the set that contains the empty set, which is different than the empty set, because this set has one element in it, namely the empty set. If you actually want to read about the foundations of set theory, where you actually trying to find the ground on which everything is built, there's a very good book by a guy named Paul Halmos called Naive Set Theory. And one of the basic axioms in naive set theory is that the empty set exists. Because you have to actually make very clear what you're assuming, what you're starting with, the rules with which you're manipulating things. So you actually have to assume that the empty set exists in order to get anywhere. And it's at this point in time, it's, talking about that sort of stuff that I really remember why I never wanted to go into logic. I like being logical. I mean, being logical is what we do, but having to worry about the existence of the empty set is just, it's not what you want to be doing at 3 in the morning after a night out. It's really not. Okay. Now, I will tell you this as a fact. I will leave it for you to try and argue yourself as to why. If I look at the power set of the natural numbers, that's the same size in terms of infinite set size as the real numbers. So here, isomorphic, just meaning there is a bijection between these two. So the power set of the natural numbers is the same size as what we call the continuum, i.e. the real line. So what I know is that I have the natural numbers here, and I have the power set of the natural numbers here, which is the same size as the real numbers, and I know these are different. And the question is, is there anything in between? Is there a size of infinity between the natural numbers, the integers, The algebraic numbers, which we defined earlier, again, have the same size, the same cardinality, to use a technical term, as the natural numbers. And that's really the fact that I have finitely many integer coefficients, is the basic idea. Takes some work, but it's just an extension of the argument of why the positive rationals have the same size as the natural numbers. So I have an infinite set here, I have a bigger infinite set here. Does there exist an infinity that lies between them that's bigger than the natural numbers, but smaller than the real line? This is known as the continuum hypothesis. People spent their mathematical lives trying to prove, no, there isn't. That the next biggest infinity after the natural numbers is the real line. Or to try and prove that it's not. And they kept falling short. Because run into one of those awkward words. There's a standard axiomatic system that we use to define math. It's known as the Zermelo-Peano axioms plus the axiom of choice, ZPC. So we have our standard axiomatic framework. And most of us as working mathematicians never worry about the Zermelo-Frankel-Peano axioms and the axiom of choice. We just never worry about it. There's a mathematician in the mid-20th century, early mid-20th century, by the name of Kurt Gödel, who proved a beautiful fact. If you have an axiomatic system of math that's strong enough to support the definition of arithmetic, so you define numbers, you define addition, then one of two things will happen. You will either have a self-contradictory system where you have statements that are both true and false, in which case everything comes tumbling down around your head and ankles and gets horribly complicated, dust everywhere, and disaster and starting over to rebuild. Or you have holes. You have statements that are neither true nor false within that system. And one of the little ironies of history, Gödel proved his result right as Alfred North Whitehead and Bertrand Russell were finishing the Principia Mathematica, which was an attempt to prove that the mathematical system that we use is both consistent and complete. It's sort of a shame that he did it right then, right before they got Volume 3 published, because it was sort of annoying to them that their entire life's work was suddenly rendered impossible, which would be a bummer. But so either we're self-contradictory or we have holes, and there's nothing we can do about that. Now we believe, although we do not actually have a proof, that the axiomatic system in which we are working, the Zermelo-Frankel axioms plus the axiom of choice, we believe that to be a logically consistent system. One of those little amusing things you can ask is, perhaps it's not logically consistent, or perhaps the shortest statement, which is both true and false, is not a statement that we can fit in the physical universe, and what the heck does that mean then? But that's a different question entirely. So we believe that our system is consistent, which means that we're going to have holes. We're going to have statements that are neither true nor false. And this is one of them. So it's not that we don't know. It's that the question is unknowable. It's, in a formal term, undecidable. There is no way to decide, unless you assume that it is true, or you assume that it is false, that there is something between these two or not. It's almost a matter of faith. If you want to do a mathematics that has an infinity between the natural numbers and the real numbers, you can do it. You just assume there is one and you go off your merry way. If you want to work in a system that doesn't, you just assume there isn't one and you go off on your merry way. And you might think that this is sort of a very abstract sort of thing. But you find weird statements. This is just where I like to close, because I suspect heads are beginning to hurt. I'd like to close with a statement that's equivalent to the continuum hypothesis that seems to me much less abstract than there exists an infinity between these two infinities. So, take a set in the plane and take a point in the plane. We say that A is a cloud based at A, around A. If every line through little a intersects the set in finite many points. So for instance, the unit circle is a cloud around the origin. Actually, the unit circle is a cloud around any point. Because if I take any point and I draw a line, it's going to intersect the circle in either 0, 1, or 2 points. So, a set is a cloud around a point. I'm not claiming that this point is in the set. I don't care if the point is or is not in the set. But the set is a cloud around the point if every line through the point intersects the set in finitely many points. Everyone think they understand the definition of cloud. So the continuum hypothesis is equivalent to the statement that the plane is the union of 3 clouds. So we have a very practical, very concrete, these are sets in the plane sort of definition. This idea of how many clouds do I need to have to put together based at, different points. So for a cloud, I have a set, I have a point. I'm asking questions about the lines through the point and how they intersect the set. And the plane is a union of 3 clouds, if and only if you assume that the continuum hypothesis is true, so that there is no infinity between these two. So this abstract question of does there exist an infinity between these two infinities actually has practical consequences in terms of things that we think we understand, like the plane. I think I've done enough damage for one day. Thank you very much for your time. If you have any questions, I'll be able to address them, either as a group or individually. And I wish you a pleasant afternoon.